Hi everyone! In this video, we are going to draw the resonance structures of some molecules or polyatomic ions, and then later on we will use these as our springboard for a discussion on picking out or deciding which structure is most valid or most relevant for a given set of resonance structures. Okay, so let's deal first with a few definitions. Resonance structures or resonance forms are those that have the same relative placement of atoms but different locations of bonding and lone pairs. Okay, but always remember that if you have a resonance structure, the actual molecule or ion is actually a hybrid of those resonance forms. So its meaning is a combination or it's an average of its resonance structures. So for example, number one, you have the nitrate ion NO3. Again, you see covalent bonding between the nitrogen and oxygen atoms. Okay, and then this is a polyatomic ion that can participate in ionic bonding, right? So our least electronegative atom is nitrogen, N, and then it's surrounded by oxygen, one, two, three oxygens, right? So when you talk of NO3, nitrogen has 5 valence electrons and there's only one atom, while oxygen has 3 atoms present in that structure and it has 6 valence electrons. Alright, so that's 5 times 1 plus 3 times 6. This is 18 plus 5, you have 23. 23 valence electrons. But you have noticed that there is a charge, so be very careful with this charge because this actually means something. Okay, it means that to the structure or to the group of atoms in NO3, there is an additional 1 charge. All right, so if it's not, the number is not reflected, it is actually 1. So therefore, the total number of valence electrons has 1 more valence electrons due to the charge, okay, because of the negative sign. So therefore, the total number is 24. So let me just write it down here for it to be very clear and you will not forget later. Okay, so you added 1. So if it's positive, then the operation is subtraction, minus 1. Alright, if it's you see a positive charge. In this case, it is plus 1 because there is 1 more valence electrons. So 24 valence electrons in total. The next thing to do from the previous discussion is that we are going to connect these atoms using single bonds, and there are 3 single bonds, so we have to subtract 6 because each single bond is made up of 2 valence electrons, and that would give us 24 minus 6, 18, right? 18 valence electrons. And therefore, we have something like this. We distribute those 18 valence electrons first to the attached or the appended atoms, which in this case is oxygen. Okay, and we complete the octet of oxygen. We know that they need 6 more because there are already 2 atoms that are shared between each oxygen atom and nitrogen, which is the central. All right. So in this case, 6 valence electrons times 3 atoms, you get minus 18, right? So minus 18 here, you get no valence electrons left, so 0. So what do we do to complete the octet of nitrogen? Okay, so we end up with this structure supposedly. Okay, so what we can do is choose any one of these, choose any one of the oxygen atoms to share a pair of electrons to nitrogen such that it will be able to complete its octet. So let's say I choose this pair of electrons from this oxygen atom and make it into another bond such that they will have a double bond in between them. Alright, so you end up with this structure O Then you have a double bond between the first atom, N, and then a single bond also. But we can also draw the LEDs, okay? We can also draw another correct LEDs for nitrogen, for the nitrate ion, which will be N, and then instead of getting from this oxygen, we get from the other one. So here O, and then this has 1, 2, 3, 4, okay? So it's just like getting this pair of atoms, or pair of electrons rather, and placing it on nitrogen, and then O here, okay? That is also another or valid depiction for the nitrate ion. Or lastly, the last pair is this one, N, and then you have O, and then O, double bond between the O and N. Okay, so in this oxygen atom already, so 1, 2. Right, so we can have that. These are equivalent structures and they mean the same thing. Okay, it's just that the electrons are being delocalized. Okay, meaning the electron pairs are traveling from one pair of atoms to the next. Okay, they're traveling from this side. So do not forget to place your uh, LEDs for ions in a bracket and include the charge in it, right? So that we will know that we are dealing with a charged particle of NO3, okay? Here. Okay, let's pretend that the arrow is outside, the negative charge, all right? In here, so negative. So those are the resonance forms or the resonance structure of the nitrogen or of the nitrate ion. Okay, these are valid forms, and then when you think of the actual molecule, when you think of the actual polyatomic ion nitrate, then it's just that the electron density will be transferring from this side to here to here. It can be any in those sides. So those are the relevance of resonance structures. All right. So I leave it up to you to have a few more examples. Why don't you try number 2, the carbonate ion? All right. So number 2, CO3, and then 2 minus. That is our carbonate. Pause this video and then try to draw the resonance forms or the resonance structure of the carbonate ion. Okay, so if you are still having trouble regarding Lewis electron structures, then we can do carbonate ion together. If you are already sure with your answer, then you may skip this process or this solution. Okay, so the central atom in this case is carbon, and it's surrounded by 3 oxygen atoms, right? So going back, so our least electronegative element here is carbon, which will be our central atom, COO, okay? And then for carbon, you have only one atom, 10 times 4, because carbon has 4 valence electrons. Oxygen, here, there are 3 atoms of oxygen, and it has 6 valence electrons. So this is 18 plus 4, you have 22. Okay, 22 valence electrons. But remember, you see a charge there in the carbonate ion. So 2 minus. So what does that mean? The total number of electrons increases by 2, right? So 2 more valence electrons, such that you will have 24 valence electrons. Okay, and then we draw single bonds to connect our central atom to the attached atoms. And then this is 1, 2, 3. Okay, each bond has 2 electrons, so 3 times 2, you have 6. So from the 24 valence electrons, 6 are already bonding. So this is 18. Okay, and if you have 18, you can distribute these 18 valence electrons first to the attached atoms, which is oxygen. Okay, and you know that each oxygen atom here, since it already is bonded to it is already bonded, so it must have 2 electrons already. So there, by adding 6 valence electrons, we have completed its octet. Okay, however, we notice that carbon has only 6 electrons on it. So 1, 2, 3, 4, 5, 6. So what do? We choose any of these carbon atoms to share their electrons, such that, for example, you have to share from this oxygen atom. So this pair of electrons will be removed and will be forming a second bond or a double bond with carbon, such that you will end up with O, 1, 2, 3, 4, something like this. All right, O, 1, 2, 3, 4, 5, 6, and then we enclose it in a bracket to represent that the molecule or the species is a charged particle and it must have gotten 2 more electrons, right? So this is one valid structure or valid LEDs for the carbonate ion. But we can also have other structures wherein the other oxygen atoms will be sharing their pair of electrons. So this is O. Okay, so the oxygen, assuming that the second atom to the right will be now sharing its valence electrons. So this is 1, 2, O. So 4 more. And then, by the way, this is carbon. And then O here, 1, 2. Okay, so we have another resonance structure for the carbonate. Okay, enclose it in a bracket, 2 minus, right? And the third structure is this third resonance structure is one wherein the bottom oxygen shares its pair of valence electrons. So we see a double bond and then 2 less electrons for the bottom carbon. And then O here, 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. And then enclose it in a bracket. 2 minus. So there you have it, the 3 possible correct LEDs of the carbonate ion. So again, the actual polyatomic ion, the carbonate, is a mixture or is an average of the 3 resonance structures. Okay, so it's just a matter of the placement of the double bonds. Okay, and whenever you place double bonds, there are less electrons present from the attached atoms. Alright, so in the next video, we will be using formal charges to choose which resonance structure for certain molecules is. Okay, and that will pave way to our understanding on the molecular geometry later on. Okay, so take a break or stretch and then have a cup of coffee.